Hi, I'm David Borthwick, and I'm a math professor at Emory University. And in this lecture, I'm going to try to explain some of the mathematical ideas behind the concepts of overtones and musical intervals. So just to give you a quick outline, after a brief intro, we'll get right into the discussion of overtones. And then I'll explain how musical intervals are built from overtones, and then the relation between the 12-tone scale and certain musical intervals. So just to introduce what we're going to be talking about, the scale that I'm going to get to at the end of the lecture is the Western musical scale, which sounds like this. So those are the 12 consecutive keys on a piano, white and black, that you play if you go up a single octave. So that scale was actually introduced by Pythagoras about 2,500 years ago. And one of the questions I want to get to by the end of this lecture is why 12 notes? Why that number and not some other number? The short answer, which we'll have to explain later, is that 3 to the 12th is nearly a power of 2. So we'll come back to that by the end of the lecture. So what Pythagoras was doing was studying the relationship between the length of a string and the pitch of its sound. And to do that, he used an instrument that looks like this. This is a modern reproduction, but it's called a monochord. It has a single string and a movable bridge. So you can fix the tension. So the tension on the two sides of the bridge is the same, but you get 2 different notes depending on where you put the bridge and what the lengths are on either side. And so what Pythagoras found using this device is that certain ratios of lengths give rise to pleasing intervals. For example, the 2 to 1 gives you an octave, 3 to 2 gives you a fifth, and so on. And in general, integer ratios between the lengths give nice sounding intervals. So that's the first question we'll try to address when we get to this discussion of intervals, is why the ratios of lengths turn out to be integers. But before we get to that, we need to talk about overtones. So the concept of overtones traces back to Vincenzo Galilei, who was actually a famous lute player in the late 16th century. And but he was also very scientifically minded, and he studied vibrating strings and tried to figure out their properties. And that work was carried on in the early 17th century by Mersenne. So Mersenne was actually a French priest, but he was also a mathematician and a physicist and a musician. And he was a friend of Galileo, who was Vincenzo's son, who was obviously much more famous as a scientist, or eventually much more famous as a scientist than his father was as a lute player. Together, they found a sort of exact law for the phenomenon that Pythagoras had observed with his monochord, which is a relation between the tension, the length, and the density of the vibrating string and its frequency. So the frequency correlates directly to the pitch that we hear. I'll talk about that a little bit more later. And they found this formula relating all these quantities. But another thing that Mersenne observed was that multiple pitches sound within each individual string note. And these extra pitches are what we call the overtones. So just to demonstrate this, let me play the C below middle C on a cello. And according to Mersenne, when that note sounds, what is actually sounding is this set of pitches shown here. So the first note is the actual cello note that we hear, which looks rather low in the treble clef, the way I've done it here. And then the next note is 1 octave up. This is a C and another C, and then a G, and then a C, and then so on. The notes get very close together as we go far up. And so Mersenne claims that all of these notes are sounding within that cello note, which is quite remarkable because we hear just a single pitch. But we can demonstrate what's going on if we think about what's happening on the string. So the overtones, the higher overtones that Mersenne is talking about, correspond to different wave patterns occurring on the string. And the wave patterns look like this. So the bottom note corresponds to a vibration basically of the string along its full length, For the second note, the first overtone, the string is effectively divided in half, and the two sides vibrate opposite each other. And for the next one, it's divided into three parts, and so on. And so we can actually distinguish the different notes of the different overtones inside the cello note by filtering. So I'm about to play you the sort of filtered version of the cello note where I've separated out all the different overtone frequencies. So the sound that you're going to hear is the actual cello note. What I've done is just cut to a range of frequencies around each overtone, so you hear only that. So there's the lowest one. There's the next one. So it does not sound like a cello at all, but all of these sounds are filtered out of that note. They're part of that original sound that you hear. And as the musical notation indicates, they start to get quite close together as you go up. So what's going on is that your brain is packaging all of those vibrations into a single image, if you like. It's basically interpreting all that information as a cello note. That's part of how you can tell a cello sound is different from, say, a bassoon or some other instrument that might be playing the same note. Is those upper overtones are audible, and your brain picks them up. But the brain also packages that information together. And a good reason for that is that a lot of our oral processing in the brain was designed to decode speech. And you can imagine it would be rather confusing to decode speech if you're hearing all of these different pitches separately. And so it's useful for the brain to put that all together into a single pitch. The same thing happens with our voices. So you might wonder how we know that those are the wave patterns corresponding to the overtones. And that's actually possible because we can play the individual overtones by singling out certain patterns using our finger. So, for example, if we want the first overtone pattern, we can block out the fundamental note. We can block out the first pattern shown here, and select the second by putting a finger right in the middle of the string, and that will cause the first vibration to be impossible, and we'll see only the second. And the fourth, we won't see the third, etc. So we'll knock out certain vibrations by putting our finger on a place where the particular pattern has a node. And so just to demonstrate this, I've recorded a little demonstration on the viola. If I just play the open string by itself, it's a D string, so mainly you hear the fundamental note, which is a D. If I want to stimulate the first harmonic, then from that sine pattern, you can see that I should put my finger in the middle of the string where the sine wave has a node. And that blocks the fundamental frequency, and I hear a frequency which is exactly double the original D, so it's actually a D 1 octave above. If I put my finger 1/3 of the way down, then I am going to produce the second overtone, which is a frequency that's a factor of 3 above the fundamental. And I can do that at 1/3 or at 2/3. Same note, because I'm reducing the vibration to the same sine wave. If I go to 1/4 of the way down the string, then you hear the third overtone, which is 2 octaves up. And for the fourth overtone, I go exactly 1/5 of the way down the string. So that was on the viola, but you get the same effect on a guitar or a harp or any string instrument where you can touch the strings. You see the same phenomenon. So to explain why the overtones have the pitches that they do, we need to talk about the relationship between frequency of vibration and the wavelength of the wave pattern and the pitch of the resulting sound. So first of all, frequency, that's the rate of vibration. It's measured in hertz, which is just oscillations per second. So just literally the number of times that the string bounces back and forth every second, that's the frequency. The frequency is related directly to the pitch, but in such a way that raising the pitch by a constant amount multiplies the frequency. Right? So it's a multiplicative relationship. So for example, an octave corresponds to doubling the frequency. The cello A string is an octave below the violin A string, and the frequency is exactly double. Here's another example. The double bass E string is 4 octaves below the violin E string, and so the pitch is down by a factor of 16. So here's a frequency plot of the cello note, where I've just separated out the intensity of the sound at each frequency. And you can see the overtones as the spikes in this picture. So the actual note is roughly 131 hertz. That's where the bottom spike occurs, and the overtones occur at integer multiples. So the next one is approximately 262, etc. They're all evenly spaced. That pattern of evenly spaced evenly spaced overtones is called harmonic. So these are harmonic overtones. Sometimes they're just called harmonics, but really they're overtones, and they're harmonic because they're evenly spaced. So now let's talk about wavelength. The wavelength is just the characteristic length of the vibration pattern that we were talking about previously. So it's measured basically the length that we take to go one complete sine wave. So each lobe of this pattern is actually half a wavelength. And the relationship between wavelength and frequency is not completely obvious, but it was explained by a mathematical model developed by Jean-Baptiste d'Alembert in 1747. D'Alembert is pretty well known as a physicist, but he was also a mathematician and also a musician. He wrote books on music theory. And he was also trained as a lawyer, which I sort of imagine is maybe what he's doing in this picture here. So he had a whole lot of things going on. This is the equation, which if you don't know calculus yet, then this might not mean much to you, but this is the wave equation that D'Alembert developed. And it actually predicts the relationship between frequency and wavelength. And so I can show you this, that the most basic solution of the wave equation has the form of a sine function, and it's a single lobe of the sine fit into the string. And that gives you the wave equation actually explains the relationship between frequency and the tension and length and so on that was observed by Mersenne and by Galilei. The next possible vibration pattern has half the wavelength and twice the frequency. So the fact that these are related the way they are, the fact that frequency is inversely proportional to wavelength is something that is predicted by this model of the wave equation. And the wave equation is just derived from basic physical understanding of how the string works. So if you go up to a third of the original wavelength, you get 3 times the original frequency. Okay, and that explains why they come in integer ratios, because in order to fit within the string is fixed at both ends, and so for these wave patterns to fit within a single length of string, they have to be 0 at the ends, and so you have to have a sort of integer fraction of the total length as the wavelength. So, one thing we haven't talked about is how do these pitches all happen simultaneously? So I showed you some individual solutions of the wave equation, which were like sine waves. And those, if you were to hear what that sounds like, that basically sounds like the filtered version of the cello note. Those sounds sound very pure and almost electronic, like the overtones that I filtered out of the cello note. The first direct observation of what the string is actually doing was made in the late 19th century. It's considerably more difficult. It's very easy to hear what the string is doing. It's considerably more difficult to see it just because the vibrations occur so quickly. So this was done by Hermann von Helmholtz, who basically developed a high-speed camera that could record the motion of the string. But that didn't really occur until 1885. And schematically, here's what the motion that Helmholtz observed looks like. In fact, this is now called the Helmholtz motion because it was kind of surprising that the string actually looks like this. So it seems a bit strange, but we can actually see it. I mean, with modern technology, we can film it even more easily. So here's a movie showing the very slowed down motion of a string. You can see the bow on the string, but it barely looks like the bow is moving because this is slowed down so much. And you can see that characteristic pattern of basically a sort of a kink traveling around in a kind of an oval up and down the string. So we claim that is basically a superposition of the sinusoidal overtone pattern. So we're putting a bunch of the different overtone patterns together in order to generate that motion that the string actually has. So let me just try to show you how that works. So here are the first two overtones, well, the fundamental note and the first overtone, the first two vibration modes of the string. And I can just add them together. So they could happen, they could happen simultaneously, and that would still be a solution of the wave equation. And if these two motions happen simultaneously, it looks like this, which already starts to, even after two of them, already starts to show this kind of oval motion that you see in the Helmholtz picture. And as I increase by adding additional modes, it gets closer and closer to that Helmholtz picture. So that's 3 modes. If I go to 8 modes, you can see it's very closely correlated to the Helmholtz observation. So what this means is that when the string is vibrating the way Helmholtz observes, and that just, that's a bit complicated to explain in terms of how the bow is gripping and releasing the string, but we could just agree that from the picture, this is what the string is actually doing. That means that all of these overtone modes are built in there. They're all happening at the same time in order to generate this motion. And so in terms of the frequency, we're hearing all of these different frequencies, the overtones, because of all of these different frequencies of vibration are combined in that one Helmholtz wave pattern. So this basic structure of the string leads to harmonic overtones, but other pitched instruments have the same phenomenon. So a violin, an oboe, a trumpet, a clarinet, they're all playing the same note. And I've graphed the frequency so that you can see the overtones, and they're all very closely related. They all have this even spacing of overtones, which we call harmonic. And but the different overtones have different intensities, and so that's why an oboe and a clarinet don't sound the same, but they both give a very strong note that we pick up on. So another good example of a pitched instrument is the human voice, which also has the same set of overtones roughly as a violin string. So if you go to a non-pitched instrument, there are still overtones. In fact, there are just too many. The overtones are more chaotic. They aren't arranged in this neat harmonic pattern. They just occur actually much more densely packed. So for example, a drum. That's what the frequency spectrum looks like. You can see actually there are overtones in there. There are spikes, but they're just many, many spikes. And same thing with a gong. A gong produces many, many high overtones, which is why it has that distinctive metallic sound to it. But so many that it's not a harmonic pattern. We can't distinguish a particular note all that well. What we get is a more sort of wash of all the overtones occurring at once. So just to summarize, a vibrating string produces overtones above its fundamental note. The wavelengths are limited to integer fractions because they have to fit within the fixed ends of the string. And this implies that the frequencies occur in integer multiples. So when that is a phenomenon that occurs for other pitched instruments. I mean, the physics is different. Obviously, for a trumpet or a clarinet, that's a different physical system that's producing the sound. But the principle of fitting waves into the evenly into the length of the instrument applies essentially to all pitched instruments. And that produces a harmonic overtone pattern. Okay, so moving on from this, let's talk about musical intervals. So these are very closely related to the overtones. The most basic musical interval is the octave, which we all hear naturally as giving two notes an octave apart naturally sound to us like the same note. So that phenomenon is called octave equivalence, where notes in different octaves are identified, and that's just a natural phenomenon that is occurs to us. I'll try to explain in terms of the overtones why that is. So here's the overtone series for the bottom note, and I've plotted it according to pitch. That is, the spacing of these notes is by pitch. And the coloring is by the note names, so that the notes in the same note in a different octave will be colored the same way, just similarly to how a xylophone is usually colored. So you can see that the C keeps recurring in the overtone pattern, and other notes start to come in as you go up. And so when you have two notes that are exactly an octave apart, the upper note has the overtone pattern shown up above in this plot. And one of the things you notice is that all of the overtones of the upper note are contained within the overtone pattern for the lower note. So that explains the octave equivalence, right? The overtones that you're hearing from the two different notes are very, very similar. And in fact, every overtone for the upper note is an overtone that you're already hearing for the lower note. So your ear just puts those together and says that's the same pitch. With other intervals, something similar is going on, but there's less overlap. So for example, the first interval distinguished by Pythagoras, other than the octave, was the fifth, which has a ratio of 3:2. And so that's what a fifth sounds like. And you can see basically that not all of the overtones of the upper note match, but every other one does. So the G's are all part of the overtone series for the bottom note C. And this D is, there's some notes that are extra, so it doesn't sound like the same note, but there is a pretty high degree of overlap. Perfect fourth means that every third overtone from the upper note is contained within the overtone series for the bottom note. So that's noticeably less overlap than the fifth. The fourth does not sound as consonant as the fifth because the overtones don't line up quite as much. Even though you could have if you put the G below the C, that would be a perfect fourth. That's not the same interval as the G above the C. All right, so the octave equivalence means the notes sound the same, but it doesn't make you can't apply that to the intervals. It matters which note is on the bottom. So for a perfect fourth, you get this amount of overlap. And if you go to less perfect intervals, then they sound interesting because there is some overlap, but there's less overlap than for the ones we've talked about so far. So there's a major third, and you can see the upper note is reinforced in the overtone series from the bottom note, so it sounds distinctive. But there are many, many more overtones that aren't quite overlapping. A minor third has even less. You can see now we need to go up higher in the overtone series for there to be a match. And there are many, many more overtones that don't quite line up. And so as you go to more dissonant intervals, the reason intervals sound dissonant is because fewer and fewer of the overtones are matching. So for example, a tritone or an augmented fourth sounds like this. And that was for a long time thought to be very dissonant, say in the Middle Ages. And there's a good reason, a good physical reason why that sounds dissonant. It's because the amount of overlap is relatively small. There's still an integer ratio there. You can still tell whether a tritone is in tune or not because it's still some matching of the overtones, but dramatically less matching than, say, for a perfect fifth. Okay, so this is just a quick discussion of musical intervals, but the idea is that musical intervals happen because overtones match between the two different notes. And if the overtones are harmonic, then they'll match when the frequencies of the bass note have integer ratios, like the ones that we just saw. So octaves are heard as equivalent and they're cases where the frequency is related by a factor of 2, and that factor of 2 causes the overtones to line up quite well. And perfect interval ratios involve factors of 2 and 3. So this is getting back to that first comment that the scale has 12 notes because that's the first power of 3, that's nearly a power of 2. So that the reason those powers of 2 and 3 occur is because those are the ratios that give perfect intervals and octaves. So let's come back to talk about the scale. So there's one bit of confusion to maybe clear up before we start talking about the scale, which is that the names that we use for the intervals refer to the major scale. So these are the common names for intervals, third, fifth. I've been using them in the previous section, come from this scale. And that's not the 12-tone scale that I was talking about before. So that scale actually comes much later, essentially after the Renaissance. And it's misleading because the fact that we name the intervals based on the scale might think that we first come up with a scale, and then we just count up the scale to decide what intervals we're talking about. And in fact, it's the other way around. The musical intervals are a natural phenomenon. So musical intervals occur because of the overlap of harmonic overtones, as we just talked about. And so there's something that happen no matter what scale we decide to use. So, for example, they're universal. All cultures hear the same intervals because that's basically built into how vibration works and how our ears detect it. So we all agree everywhere in the world that two notes an octave apart sound the same. And we all distinguish a fifth as a special interval. But scales are very much particular to different cultures. And so the scale is somehow artificial, right? So instead of deciding on a scale and then using that to build intervals, what we do is we start from intervals and we decide that we want a scale to highlight certain intervals. And so Pythagoras thought that Pythagoras is responsible for the notion that the fourth and the fifth are perfect. As we see, that just means the ratios involve only 2 and 3. And so, there's not, why that is so much more perfect than a ratio of 5 is a matter of taste. But that was Pythagoras' idea, that ratios involving 2 and 3 are somehow perfect, and so the scale should be built from these. So to construct the scale, you just start with the bass note, pick whatever note you like, and keep adding fifths. So there's a bass note D. I'm going to add a fifth below and a fifth above. And so on. And it's not an accident those are the strings of combined strings of a viola and violin. I mean, this system is built into our Western notion of music, and it affects how we build our instruments. So we keep adding fifths. At that point, when we have 5 notes, using octave equivalents, we could arrange them into a consecutive scale, and it would sound like this. So that probably sounds familiar to you. That's called the pentatonic scale. And this isn't the only way to come up with it. In fact, the pentatonic scale was invented independently by many, many different cultures because it's a very natural set of notes that there are various different ways that you would create that because we all hear the same musical intervals. And it proves to be a great combination of enough notes to generate nice melodies, and few enough that it's hard to go wrong, right? If you use those notes and try to generate a melody, it's kids usually try doing this on the black keys on a piano, form a pentatonic scale, and you know that if you just tinkle around on the black keys, generally it's fairly pleasing. It's hard to come up with something that doesn't sound pretty good when you use that scale. So that might have been a good place to stop, and for a lot of folk music, that is where you stop. You just use the pentatonic scale, and it generates a lot of good melody. But Pythagoras kept going, kept adding fifths. And so the next question we need to sort of figure out is why stop at a particular point? You could just keep adding fifths on the side there. So in order to see that, we need to put all the notes into the same octave. So using octave equivalents, I'm going to move all those ratios back into the original. So I'm graphing these where the height of the bar here corresponds to the string length, and so the higher notes are getting shorter, and the color is again colored like a xylophone, so the same note has the same color in different octaves. And what I'm showing up above is the actual ratio of frequencies above the bass note. So we add an A at a ratio of 3/2. The G that I originally added was a fifth below the D, so that was a ratio of 2/3. But then I moved it up an octave, so it becomes 4/3 when it appears in this octave. So I keep going like that. And after 12 notes, you've added these ratios. And the numbers keep getting higher, of course, because you're multiplying by 2 or 3 every time. So you get some funny looking ratios like this G sharp here. And that is the point where Pythagoras says to stop. And the reason is that adding one more note would cause a problem. So you can see that these are, roughly evenly spaced. They're not quite even, but they're roughly evenly spaced. If we add one more note, it's going to get close to one of the ones we already have. So here's what happens. So I can add an A flat would be the next note that I would put in by the construction. And its ratio is not quite the same as G sharp, but it's very close. Here's what it sounds like. So you can hear that was the G sharp first, which is slightly higher, and then followed by the A flat, which is slightly lower. And you can hear the difference, and it not very pleasing to have that clash in the middle of your music. So Pythagoras decided to stop with 12 notes just to avoid that. So that break between the two is sometimes called the Pythagoras comma, the gap between those two notes. And so the scale works quite well if you stay close to the original D, then you get a lot of perfect fifths nearby. But what this shows is that you go too far and the notes start to disagree with each other. So 12 is the point where that really starts to happen, and that's why you stop at 12. So let's go through the math behind that. So let's go through the math behind that. So as we said, a perfect fifth has a ratio of 3/2, and octaves are related by power of 2. And so if you add 12 perfect fifths, you keep raising the frequency until you get to 3/2 to the 12th. That's almost a factor of 130. And that's almost 7 octaves, because 2 to the 7th is 1/28. So that's the point at which you choose to stop, where you've almost closed the circle. This Pythagoras construction is called the circle of fifths. After 12 steps, it sort of appears that you close the circle. But of course, not really, because this isn't really, 130 is not really 128. And so this is just an approximation, which is a bit ironic because, the whole idea of Pythagoras is perfection in this construction. And you're using only 12 notes just because approximately 3 to the 12th is a power of 2. And there's no way it could ever be perfect, right? 3 is any power of 3 is always an odd number. And so that can never equal a power of 2. So the circle could never close. No matter how many notes you put in there, it's never going to work. So it's an interesting phenomenon that it works pretty well at 12. And that turns out to be a good number of notes. That's kind of convenient. As I mentioned before, the next number would be 41. And that is a bit impractical if you're going to try to build a piano, to have 41 notes within each octave. All right, so Pythagoras' scale became the standard tuning system in Europe for about 2,000 years. And so, this is how you would tune an instrument like a lute or a guitar, any instrument that needed to actually have assigned pitches to it would use the Pythagorean system. But many of the notes in the Pythagorean intervals are out of tune. So for example, a lot of the fifths are perfect, but some of them are not. So G sharp above an E flat is meant to be a fifth, but you can see the ratio is actually not, the ratio is meant to be 3/2, and it's not that at all. It's not even close. So some of the thing, if you go too far from the original note, some of the intervals don't sound very good. So it's 1.48. That's not, that's enough that you can hear it and it would sound out of tune. So in the Renaissance, music started to have a lot more thirds built into it. And the Pythagorean scale does particularly poorly with thirds. So it's designed to make the fourths and fifths in tune. And because the ratios are only 3 and 2, that doesn't work well for a third, because a third, if you remember from our discussion before, the frequency ratio for a third should be 5/4. And 5 is a prime number, so there's, of course, no way you can really get that if you're only using powers of 2 and 3. So what Pythagoras assigns to that 5/4 ratio is 81/64. So in the late Renaissance, new schemes were developed. And these were particularly common in the Baroque era. This is usually called just intonation, or which means really true intonation. And the idea is just to modify Pythagoras. So you stick with the 12 notes of Pythagoras, but you just retune them to try to make the thirds better, essentially, to try to make some intervals better. And so in the Baroque era, there were lots of different schemes for doing this. So one of them was called the well-tempered intonation. And so, for example, you may know Bach wrote a set of preludes and fugues in all 24 keys called the well-tempered clavier. And so that was actually, that title refers to a specific intonation system, which is a version of just intonation. And it was a method for tuning a keyboard. And but there were other systems in use at the time also. But still, the ghost of Pythagoras persisted, and we kept the 12 notes. We just tried to readjust the ratios slightly. So one way you can try to understand just intonation is that you take the notes given by Pythagoras and you try to write them with ratios with smaller denominators. Smaller denominators means that the overtones line up better. So mathematically, you can sort of understand the move to just intonation is just kind of reducing the integers used in these fractions for the frequencies. So justination actually corresponds to something that we do naturally. When we tune intervals by ear, say when we're singing or playing a violin, we naturally try to match the overtones. You know, our ear tells us if something's in tune, what's going on is that our ear is picking up on the overtones lining, matching. And so just intonation kind of happens automatically if you're listening for the overtones. The trouble with that, though, is that that only works in a single key at a time. So, for example, in the picture we just showed, the ratio for G sharp over F ends up being 7/6. So that's what it would be in the key of D, because those notes are tuned relative to D, not to each other, right? But if we did tune them to each other, say if we were in the key of F and we were tuning the upper note to the F, well, we probably call it an A flat in that key, and the ratio should be a minor third, which is 6/5. So the point is that because some of these are prime numbers, we can't possibly get the ratios to work in all different keys. There's just no way for the tuning relative to a D to be the same as the tuning relative to an F. And this is actually something that Bach was exploiting in those preludes and fugues from the Well-Tempered Clavier. Part of the point of that project was that the just intonation sounds different for different keys. So each key had its own character, and some of them sounded more dissonant and some of them sounded more consonant. And Bach was really playing with that. So you can still hear what that sounds like there are harpsichords that are tuned using the actual well-tempered system, and you can still hear what that sounds like. It's not meant to demonstrate that all the keys are the same. It's actually quite the opposite. It's meant to sort of highlight how the individual keys work. So the modern solution, though, is something called equal temperament. So the idea is we want to move around freely, and in sort of starting from the classical era onward, we started to need to modulate between keys and change keys frequently within the same piece. So we want to move around among the keys frequently, and it's a problem if we have, for example, a keyboard that sounds out of tune in some keys and in tune in others. So the modern solution is something called equal temperament, where we just even out. We take the Pythagorean notes and we just even them out. And so the ratios are all irrational numbers, which would have horrified Pythagoras, who was very much into rationality and integers. But it makes it so that every key kind of works the same way. So in some sense, it spoils what the well-tempered system does. It makes the keys all essentially identical. But on the other hand, it allows a lot more freedom for us to sound okay in after modulating from one key to a different one. So in equal temperament, we actually make all of the intervals that aren't octaves out of tune, which sounds like a bad idea, except it's only slight. It's barely detectable. So, for example, the frequency ratio for a third in the equal temperament comes out to the cube root of 2, which is about 1.26. And what it should be from from your overtone series, what it should be is 5/4. So it's not too far off. And the fifth is even better. I think if the fifth were way out, then this would not have been the system that we adopted. But for the fifth, the actual ratio that we use is 2 to the 7/12. But that turns out to be very close to 3/2. And so it's barely detectable that the fifth is wrong. So on a modern piano, most modern pianos are tuned by equal temperament. And when you count up 12 fifths on a modern piano keyboard, you get exactly 7 octaves. And so the reason for that, the way that happens, is that the fifths are all slightly wrong, right? The fifths are all slightly flat. And so after 12 of them, you come up exactly 7 octaves instead of approximately 7 octaves. So we just pretend that this circle that Pythagoras constructed, we just sort of shift it slightly so it actually does form a circle at the cost of making it slightly out of tune. So just to end, I want to point out that this equal temperament was not the only possible solution. So one alternative, in the 18th century, people trying to figure out a way to have keyboard instruments be better in tune than equal temperament. And one solution was something like this, where if you can see that there are actually, I believe, 6 rows of keys here, and each one is tuned according to just intonation, but from a different scale. So that if you play, like for example in C major, maybe that would have been the middle one. So if you play sort of perfectly in tune in C major in the middle keyboard, and then if you want to modulate, go sharp or flat, then you would have to switch to one of the alternate keyboards. So as I imagine that as you modulate upwards, you would move up to the upper keys, and if you modulate downwards, you would go down to the lower keys. So there are obvious reasons why that didn't catch on, because you need a huge bank of strings in there to accommodate all these extra notes, and it's tremendously impractical. And I would also guess that it must have been just impossible to tune, right? Because you're having to tune, instead of the usual set of piano notes, you're having to tune 6 times that many strings. So instead of that, we use the equal tempered system, and so that's where the 12 notes come from in our system. Originally, the idea of Pythagoras was to build it all out of perfect fifths, and since then we've abandoned the notion of the perfection of those intervals in favor of keeping 12 notes, which was, you could think of originally something of an accident. So that ends this lecture. Just to sort of finish up this discussion, you might, if you're familiar with the piano, you can go to the piano and count up 12 fifths, and you'll notice that on a piano, 12 fifths are exactly 7 octaves. So you might wonder what's going on, because I just told you that that's not true. And the solution is that your piano is not in tune. The octaves are correct. So, assuming your piano has been tuned professionally and as tuned as it's ever going to be, the octaves will be correct, but the fifths are not. The fifths are actually slightly flat. That is, they're slightly too narrow, because if you did 12 actual fifths, you'd end up a little bit above 7 octaves. So it's a compromise. In order to build actual instruments, we make some of the intervals wrong. The same thing happens with guitar. We make some of the intervals incorrect in order to basically pretend that what Pythagoras's circle of fifths, actually works. All right, I'm going to stop at that point. If there are questions, I'd be happy to answer them.
Thank you, David. That was very, very fascinating. I appreciate you sharing that with us. Let's give David Borthwick a hand, everybody. Applause for him. David's at Emory, and we're very happy to have him here for Mathapalooza. So I haven't seen any questions in the chat directly for David, but I encourage you all to, if you have a question for him, please bring it up. I'm going to ask you a question about this sort of music theory math thing that I was thinking about. You know, people talk about half steps and whole steps, right? In your scales,
Right.
and this is sort of maybe an off the wall question because I'm not sure it's exactly related to what you're talking about, but it's definitely in this space. So, if you take a piece of music, say written, and you say between any two notes, whether they're quarter notes or whole notes or whatever, between two consecutive notes in a single melody, there is either let's say it's either moving up a certain number of steps or down a certain number of steps. One could imagine that you could make a reflection of that, whatever that delta is, and instead of the notes going up a half step, up a whole step, it would go down a half step, down a whole step, and you'd sort of have a mirrored piece of music. I'm wondering if that, I'm sure it must have been done in the music theory world, if that has a name or if that's something that still sounds good to the human ear.
Yeah, I mean, in fact, one of the people who played around with that the most was J.S. Bach. So he loved to take his melodies and invert them, which would be to turn it upside down the way you're describing. Or he would also do a retrograde, which is to play them backwards. Or he would do a retrograde inversion to play them backwards and upside down. And so he, you know, if you look in his pieces, you know, they're sort of like little puzzles hidden in some of Bach's pieces that, you know, as you're listening, you just think it sounds like beautiful music. But then when you look at what's actually written there, you see that, oh, he's taken this part and he's turned it upside down for this part, or he's now playing it backwards. Or, I mean, he does other things with the time, which is to sort of elongate the time, double the time, or reduce the time to half. He does all these little sort of puzzles in there. And they're not always obvious to the ear. They're sort of like inside jokes, right? They're sort of inside mathematical jokes. When you look at the music, you see, oh, he's actually doing this. So.
What got you interested in this kind of stuff?
Well, I guess you know, I've been playing music. I've been playing the viola since I was 8. I've been playing music much of my life, and always been fascinated by that. And really that kind of translated into a lot of my mathematical interests. I became interested in, you know, oscillations and spectral theory and the, you know, the study of frequencies of vibration, partly because I am so into music. So it kind of was the music that drove me into this kind of mathematics rather than the other way around.
Interesting. That's great.
But I like looking back at all these historical figures who, you know, really, you know, Mersenne, you could have said that he was just a musician. We think of him, a lot of mathematicians think of him as a number theorist, but he was, I mean, you know, just as much a musician, or just as much, he's considered the founder of modern acoustics by people who do acoustic. I mean, he just, I kind of like this era where people could kind of combine all these different things together.
Yeah, nice. If anyone else has any questions for David, we got a couple more minutes. We can certainly put them in the chat. But we're really happy to have you join us, David. It was really great. I feel like I have to go brush off my guitar and tune it not quite properly now.
That's right.
I just sent a question.
Oh yes, yeah. Question in the, is this maybe you can just unmute and share it with us? I'm not seeing it in the chat.
Pentatonic scale you can find on the piano keyboard just by pushing the black buttons. Is that correct? Or?
Yes, that's correct. That's probably the easiest way to sort of find a pentatonic scale on the keyboard, is that the black keys.
That makes it easy for
we'll do that.
So to play nice melodies.
Yeah, there's an etude by Chopin that's called the Black Key Etude, where he just uses only those black keys, and so it's obviously pentatonic.
Definitely. Okay. Any other questions? This is your opportunity. You've got the math music expert here. Okay.
All right.
Well, again, I want to thank you, David. It's been great. We got about 2 minutes left in this session, and then I'll give you guys some more announcements in just a minute. But I want to take this opportunity once again to give a big welcome or a big thank you to David Borthwick